Let us start by examining a simple bar magnet that might be represented like so. Here is north of this magnet and here is south magnetic pole. There is going to be magnetic field around this bar magnet, and the field lines emerge from north pole and they are terminated at south pole, like so. Perhaps there is another line that looks like this, once again emerging at the north magnetic pole and being terminated at the south magnetic pole. And of course, on this side, the same is happening. You have to visualize this is three-dimensional phenomenon. This is a simple bar magnet that you might find on your refrigerator. So the question is, how is this relevant to our planet Earth that is a spherical object like so? Well, it turns out that magnetic field lines around our planet resemble to a certain extent magnetic field lines of a bar magnet. If there was no sun, which I will discuss in several minutes from now, if there was no sun, then magnetic field lines of our planet would be actually very, very similar to these. They would emerge from somewhere here close to South Pole and they would terminate somewhere close to the North Pole. So we would have lines like so. Whereas I'm assuming that this over here is the North Pole, let's call it NP, and this over here is South Pole, let's call it SP. Now here by NP I mean North Geographic Pole, or also known as true north, and SP is South Geographic Pole, or also known as true south. And you can see that purposely I displaced the location of termination and emergence of magnetic field lines from true south and true north. I did it because magnetic poles on our planet do not coincide with geographic poles on our planet. So this over here we called North Magnetic Pole, this point over here, whereas this point over here we call South Magnetic Pole. And North Magnetic Pole is currently situated somewhere in the north Canada, I think 86.5 degrees north and around 164 degrees east, but it is changing, it is moving. It is moving indeed over very long periods of time. It will not move much over our lifetime, but nevertheless it is moving. Currently, I read it is moving towards Siberia at a certain velocity, but many millions of years ago, actually North Magnetic Pole was over South Pole and South Magnetic Pole was over North Pole. In other words, the polarity of our magnetic field reversed. Now, magnetic field of our planet is rather weak. It is between 25 to 65 microteslas. You know that this is a symbol for micro, 10 to negative 6, and Tesla is a unit for the strength of a magnetic field. But Tesla is a very large unit. It is very difficult to create magnetic fields of several Teslas, 1, 2, 3, 5, 7 Teslas. So that's why people also introduced another unit known as Gauss, G, and then in this unit of Gauss's, magnetic field of our planet is between 0.25 and 0.65 Gausses. So you can see, you can find now clearly, simply relationship between Gauss and Tesla. Now, I would like to discuss two more things here related to magnetic field of our planet. Number one, you will notice that in this figure, magnetic field lines originate from south magnetic pole and are terminated at the north magnetic pole. Whereas for the bar magnet, I said that the north pole is the source and the south pole is the sink. It seems to be different here. It is really, if we want to be technical, it is not different. It is just a matter of labeling. You see, indeed, magnetic south, true magnetic south, is here, close to the North Pole. True magnetic north is here, close to the South Pole. But because people didn't want to call magnetic north close to the South Pole and magnetic south close to the North Pole, they relabeled true north to be south magnetic pole and true magnetic south to be north magnetic pole. So it's just matter of labeling. I didn't invent this convention, I'm just telling you how it is. But in many cases that doesn't matter, because at the end of the day the direction of these field lines, in many cases, not always, does not matter so much. So that's the first thing I wanted to discuss, technical thing. The second one is what is creating this magnetic field around our planet, because our planet is not magnet like bar magnet. Well, what is creating magnetic field around our planet has to do with the core of our planet. You see, our planet has inner core, of course, that is very, very warm. In particular, the inner part of the core is so warm it is molten lava. The outer part of the core is cold, still very warm, but cold enough to be solid. And it is mostly iron. I am representing it with black here. Now, this molten lava, which is green here, cannot produce on its own magnetic field. For technical reasons, this is fundamental playlist, for the reason that the temperature of this material exceeded the Curie point. I will discuss this one day in more technical details in my advanced playlist on Thursday. At any rate, what we have here is the thermal currents, heat, being transferred radially from the very, very hot inner core. Now, when these thermal currents enter the region of iron core over here, this black region, they continue propagating, but because Earth is rotating, this iron core is also rotating, and it is rotating faster than the inner core, which is very important for the formation of the magnetic field. Now, when these thermal currents enter the, as I said, the iron core, they can be transferred into electrical currents. Now, the moment we have electric current, that means we will have magnetic field associated with electric current if you study electromagnetism. And these currents, electric currents, that are consequence of these thermal currents, are responsible for this rather weak magnetic field around our planet. Again, I'm skipping some technicalities because this is fundamental playlist. I don't want to go into equations. Maybe I will do it in Thursday's advanced playlist, but this is in qualitative way the source of magnetic field around our planet. Now, what I would like to discuss is how this idealized magnetic field around our planet is modified by the presence of the sun, because in reality this is not how the field lines around our planet look like. Let us see how they look like when we have our star, the sun, close to us. If we have the sun somewhere here, and what I am plotting here is of course not to scale, and here is, let's say, our planet Earth, then the sun is, in addition to radiation, also emitting charged particles in all directions. And of course, some of them will collide with the planet Earth. Now here, this is not radiation. I'm not talking about radiation here. Check my video on the characteristics of the sun if you want to learn more about radiation. These lines schematize solar wind. So what is solar wind? Solar wind are charged particles emitted or ejected by the sun that travel in all directions, and some of them therefore travel towards our planet Earth. Speed of solar wind is very, very large. Of course, it is not close to the speed of light, like the radiation. Speed of light is 300,000 kilometers per second. Solar wind, which are charged particles, has velocities between approximately 200 and 400 kilometers per second, with average being around 800, the average being 400 kilometers per second. So they move between 200 and 800 kilometers per second, with the average around 400 kilometers per second. And these charged particles are typically electrons. So electrons zip through space, and some of these electrons will now collide with the Earth and Earth magnetic field. Due to this interaction, the Earth magnetic field ends up looking more like this. In other words, you can see that there is very long tail of magnetic field in the direction away from the sun, whereas the magnetic field lines in the direction towards the sun are very compressed. Of course, keep in mind that these lines have to connect somewhere. They have to connect somewhere, who knows, somewhere over there, close to my neighbor or somewhere. Now, this is what we called magnetosphere. Of our planet. And this magnetosphere has two regions. This is tail region or magnetotail, and this is the bow region facing the sun. So you can see, instead of symmetric magnetic field that we would have if there was no sun, and what I discussed in the previous slide, we actually have non-symmetric field that creates magnetosphere, where the magnetic field lines towards the sun are compressed and they are elongated in the direction away from the sun. And they actually extend beyond the orbit of the moon. Perhaps moon is somewhere there. Moon is encompassed by the magnetic field lines of our planet. Now, when we understand this, let us finally go back and discuss how interaction between these electrons and these magnetic field lines of the magnetosphere, typically in this region, as we will see, results in the formation of northern light or Aurora Borealis. Let us now have a closer look at the mechanism responsible for northern light. Here is the northern hemisphere of our planet, and here, somewhere far away, is the sun. And the sun, as we saw, is emitting charged particles, electrons and ions that are traveling towards our planet. This is the solar wind. We also saw that we have magnetic lines, like so, associated with the bow part of the magnetosphere, and here we have magnetic lines that are stretching far away from the planet Earth that are associated with the tail of the magnetosphere. It is also important to notice that in this representation, of course, this side of the planet that is facing the sun will be in daytime, and this part of the planet that is facing away from the sun will be at night time. Aurora typically happens here, in the night side of the planet, and typically at the heights between 80 and 250 kilometers. It is very rare to have aurora at higher elevations or lower elevations. Now, how is this light emerging over here? In the following way. You see, these electrons are traveling and they start interacting with the magnetosphere. They start interacting. Why? Because they are charged particles, and charged particles interact with magnetic field in a way that magnetic field cannot change the speed of the moving charged particle, but only the direction. In other words, if these particles were moving at 400 kilometers per second, they are still going to move at 400 kilometers per second, but magnetic field lines will deflect them, and let's say this electron over here will start spiraling towards the surface of the Earth. This electron over here will be deflected back towards the Earth at the same speed, or 400 kilometers per second, but it's not going to go forever over there, but it's going to be reversed to move towards the Earth. Now, these electrons, as you can see, have very high energy. They move at very high speed. And when they start moving towards the planet Earth, they collide with molecules and atoms of the air at those heights that I just said, typically between 80 and 250 kilometers. Now, what happens when this electron impacts a molecule or an atom in the atmosphere? Well, what happens is that these molecules and atoms get excited. And I talked in one of my previous videos what that physically means. That means that electrons are bumped up to higher electron shell or orbit. These excited molecules and atoms will then de-excite and emit radiation. That radiation is sometimes in the visible part of the spectrum, and if that happens, well, that visible light that is emitted when these atoms and molecules de-excite is what we call northern light or aurora. Aurora Borealis over northern pole and Aurora Australis over southern pole. You see, if these electrons do not have high speeds, then maybe they will excite still these molecules and atoms, but when they de-excite, the energy is not high, the energy that they emit in form of radiation is not high enough to be in the visible part of the spectrum. Perhaps it is in infrared part of the spectrum or microwave part of the spectrum, and we cannot see it with our eyes. We can only see it with these, when these particles are A, numerous, and B, very energetic, and then when they collide with these molecules and atoms over there. When are they energetic and when are they numerous? When we have high activity of the sun, many explosions on the sun, and please check my video on the characteristics of the sun to understand these concepts more. Now, different light indicates that different molecules or atoms were de-excited. For example, oxygen O is typically associated with actually greenish color, whereas nitrogen N is associated with blue color, red color, and pink color. And neon is associated with the orange color. So you can see that when we observe now aurora, we can also now visualize which molecules, or rather atoms in this case, as I wrote it, are responsible for the emitted light of these excited molecules, excited due to interaction with very high energy electrons and ions coming from the sun. Can we forecast northern light? Yes, we can. Let us look into it more in the next slide. If we go back now to these beautiful photographs, then you can now visualize the collision of these high energy particles of solar wind with molecules and atoms at these altitudes between 80 and 250 kilometers. And in this case, it's a green color, which means oxygen is predominantly emitting that radiation after being de-excited. Here we have oxygen in green, and a pinkish color is related to nitrogen, as I said a few minutes ago. Now, it turns out that indeed these phenomena can be forecasted. Here we see a forecasted in terms of the probability of aurora between low and high, provided by the NOAA, National Oceanic and Atmospherical Association Space Weather Prediction Center in the United States of America. Here is the map of North America, United States and Canada, and red is high probability of aurora, whereas green is somewhat low probability. Sorry. And the forecast is usually given in terms of the so-called KP index, which ranges between 0 and 9. 0 to 3 is very, very low probability. 3 to 5, low probability, and then between 5 and 9 is higher probability. The closer we are to 9, the higher the probability. And we also have the so-called NOAA G scale, which is a little bit normalized KP. It ranges between 0 and 5. When KP is 5, then this NOAA G scale is 1. When KP is 6, G scale is 2. When KP is 7, as you can see, G scale is 3. And for the values of KP below 3 and 3, G scale is simply 0. We can also predict how far south the aurora will be observed. Again, I am using information provided by the NOAA Space Weather Prediction Center, situated in Boulder, Colorado, in United States. And again, predictions are in terms of the G index or KP index. Lastly, aurora is not only observed on our beautiful planet Earth. In fact, any planet that is rotating and has magnetic field can produce aurora if there is a sun, if there is a star next to it that is emitting particles of solar wind. So here you can see rings of the Saturn. So this is Saturn, and you can see beautiful aurora over the pole of the Saturn, sun in the distance over there. And here is once again aurora over Jupiter. As I just said, the prerequisite to have magnetic field for a planet is to rotate. Planet has to rotate to have magnetic field, at least through the mechanism that I explained earlier in this video. So now when you observe Aurora Borealis or Aurora Australis over southern pole, try to visualize what is happening in the higher regions of the atmosphere, and when you see the color, try to identify through what I just discussed, what are the molecules and atoms that are emitting this light. If you do it, please comment in the comment section below. Please make sure to like and share this video, and I will see you in the next video on the fundamentals of weather and climate. Goodbye.